Exponential growth and decay models. Uninhibited growth can be modeled using this equation. N of t equals n sub 0 times e to the kt, where k is greater than 0. Let's use that for this problem. The size p of an insect population at time t in days obeys the function p of t equals 100 times e to the 0.04 t. So we are given this equation or function for uninhibited growth. P of t equals 100 times e to the 0.04 t. We first want to determine the number of insects at t equals 0 days. That means t is 0, so p of 0 equals 100 times e to the 0.04 times 0, or 100. So we will have 100 insects at time 0, or 100 insects to start with. Next, what is the growth rate of the insect population? Okay, so our growth rate is our k, 0.04. So k equals 0.04. As a percent, that would be 4%. What is the population after 100 days? Here we're looking for p of 100, so time equals 100. So let's substitute 100 in for t. 100 times e to the 0.04 times 100, or 100 times e to the 4th, which is about 5,460 insects. Finally, when will the insect population reach 1,000? So here we know what the end result is. So 1,000 equals 100 times e to the 0.04 t, because we want to know when. We are solving for t. To solve this for t, we'll start by dividing both sides by 100. We'll get 10 equals e to the 0.04 t. And now, we'll continue solving on the next slide. We can take the log or natural log of both sides of this equation. We could have also just converted it to log form. Either way works. So the natural log of 10 equals the natural log of e to the 0.04 t. I'm going to use the log property that allows me to bring the exponent out in front. So the natural log of 10 equals 0.04 t times the natural log of e. The natural log of e simplifies to 1, so we have the natural log of 10 equals 0.04 t. We almost have t by itself. Let's divide both sides by 0.04. And t equals the natural log of 10 divided by 0.04, where t is approximately 57.6 days. Okay. A colony contained 2,000 bacteria at 6 a.m. and 3,000 at 8 a.m. How many will there be at noon? So we will use this function, and n of t equals n sub 0 times e to the kt. The information that we're given, we're going to consider 6 a.m. to be time 0. That means 8 a.m. will be t equals 2. So then we have n of 0 equals 2,000, n of 2 equals 3,000, n of 0 is the same as n sub 0. So how many will there be at noon? We will get to that in a moment because we do need to find, at this point we would have two unknowns. We would not know k or t, so let's find k using the information that we are given. So we will substitute in 3,000 equals 2,000 times e to the k times 2. Divide both sides by 2,000. 1.5 equals e to the 2k. Convert this to log form. The natural log of 1.5 equals 2 times k. Divide both sides by 2. K equals the natural log of 1.5 over 2. And technically, this is the value I would use in the function. We could find a decimal approximation, approximately 0.2027325541. And even though I might write that down, I usually keep in my calculator the exact number. So how many will there be at noon? That means, so noon is 6 hours after 6 a.m., so time is 6. So we want to find n of 6. Let's look at that on the next slide. So n of 6 equals 2,000 times e to the, and here I'm using the exact number for k, the natural log of 1.5 divided by 2, and then for t we are substituting in 6. So this is n of 6 equals 2,000 times e to the 3 times the natural log of 1.5, which is approximately 6,750. So that would be the size of our colony at noon. Okay, so let's go back to the last slide for a second. Now we want to look at when will there be 10,000 bacteria. So going back. So now we know the end result, 10,000. 10,000 equals 2,000 times e to the natural log of 1.5 divided by 2 times t. We'll divide both sides by 2,000. 5 equals e to the natural log of 1.5 over 2 times t. We will write this in log form. The natural log of 5 equals the natural log of 1.5 divided by 2 times t. We will divide both sides by the natural log of 1.5 divided by 2, which is the same as multiplying both sides by the reciprocal, 2 over the natural log of 1.5. So t is equal to, this is the exact answer, 2 times the natural log of 5 divided by the natural log of 1.5, which is approximately 7.9387 hours. Okay, uninhibited radioactive decay. So we had looked at growth, now let's look at decay. So that equation could be written in the form a of t equals a sub 0 times e to the kt, which looks like what we saw before, but here k is less than 0. So k is negative. So here is a problem where we will use that. We initially have 2 kilograms of some radioactive element, and in 7,250 years, there will be 1.5 kilograms left. Determine the exponential decay equation for this element. Okay, so we initially have 2 kilograms. That means a sub 0 equals 2. We are looking at a time of 7,250 years. A of 7,250 will equal 1.5, because we have 1.5 kilograms left. So we want to know k so we can finish writing this equation. So a of t equals a sub 0 times e to the kt. Finding k, let's substitute in what we know. 1.5 equals 2 times e to the k times 7,250. Divide both sides by 2. 0.75 equals e to the 7,250 K. Rewriting this in log form, the natural log of 0.75 equals 7,250 K. We'll divide both sides by 7,250. K is approximately equal to 0.0000396802859. In my calculator, I would probably leave the whole thing, even though I will write the decimal or part of the decimal here. So our function could be modeled using a of t equals 2 times e to the negative 0.0000397 t. Actually, I think I left off my negative sign here. That's why I paused. So hold on. I have it right in the function. K was equal to approximately negative 0.0000396802859. Okay, so next we'll look in blue at how long will it take for half of the element to decay. So half. So A of t will eventually be 1 kilogram since we started with 2 kilograms. Looking at that in blue on the next slide and substituting into our function, 1 equals 2 times e to the negative 0.0000397 t. We'll divide both sides by 2. 0.5 or 1/2 equals e to the negative 0.0000397 t. I will rewrite this in log form as the natural log of 0.5 equals negative 0.0000397 t, and divide both sides by negative 0.0000397. T is approximately equal to 17,468.3 years. Okay, so we have one more part. Let's go back to that other slide. We will look at this final part in green. So how long will it take until there are 250 grams of the element left? Okay, so that means we'll have 250 equals 0.250 kilograms. Sorry, we're given grams and everything else we've dealt with has been in kilograms, so we needed to convert. So 250 grams is equal to 0.250 kilograms. We need to make sure we have constant units in our equations and functions. So 0.25 equals 2 times e to the negative 0.0000397 t. Dividing both sides by 2, we have 0.125 equals e to the negative 0.0000397 t. Rewriting this in log form, the natural log of 0.125 equals negative 0.0000397 t. Dividing both sides by negative 0.0000397 yields that t is approximately equal to 52,404.9 years. So it will take that long for half of the substance to decay.